One of the things that confuses me the most is that we don't really understand what gravity is.
Science can describe how gravity works, but can they describe why it works?
Can we?
In science, if we can describe how something works and predict its future behavior, we claim to understand it and we move on. But I'm good with what I've done, and I can land a spacecraft on Mars inside of a crater in a hole-in-one using my understanding of gravity, so I'm pretty good with it. Okay? That's the map of dark matter. It's something out there that has 85% of the gravity of the universe, and we don't know what the hell it is.
That's not confusing?
It's not confusing. It's
If you don't know what
General Relativity has been repeatedly confirmed and under many ways overcomes Newtonian gravity. However, we are also aware that in the scientific method, a wrong demonstration is worth much more than any agreement, since agreements don't make the theory true. Our gravitational model seems to work fine up to the scale of a solar system, but they already fail with galaxies. There is a huge discrepancy between our models and the observations. So it shouldn't be questioned the existence of the problem, but how to solve it. Even worse, here we are looking at a very specific galaxy because the range of disprovements is wild. You can modify your model to fit some of them, but you still end up with contradictions in many other cases. We currently have hundreds of attempts, and the two big actors filling the void in most of our models are dark matter and dark energy. Combined, they show how much we are missing at cosmological scale. The gap is huge, regardless of name, and is not even uniform, meaning something must be really wrong. There are at least three main ways to face the problem. Gravity is okay, and there is something additional, existing or becoming evident only at larger scales. This stuff is at best weird, because it looks like gravity and have no measurable cause or source. It affects the movement of masses, but it doesn't interact neither with light nor with matter. It's worse than trying to catch a ghost. It is also possible that gravity is not consistent, but these changes always occur out of our reach. Meaning, to us, gravity is consistent from a single particle up to a stellar system, but that would no longer be true at very large space-time scales. The third option goes beyond what we have seen so far, and can downplay the need for the other two. It's not physics hiding in plain sight, it is us knowing gravity wrong. But without very large space-time intervals, we can't see the mistake. This means that our model can be wrong even where it seems to work, and before looking for something more, we can double-check what we have. This is the Einstein field equation, and to make it simple, we initially neglect the lambda term, since this is very small even within a stellar system. On the left we have the Einstein tensor, and on the right the energy tensor. This encompasses a wide range of effects as stress energy and pressure, beside waves as light, the invariant mass, and also momentum. On the left we have the geometry of space-time, and starting with a flat plane, it can be observed how energy can modify the shape of the geometry. We call this space-time curvature, and it represents the effect of gravity. Depictions of curvature are anyway difficult, and looking at the simplest interactions, the free fall, the issue is evident. These two lines are the same geodesics. The one in 3 dimensions is what we see, while with 4 dimensions we have the curvature of GR. And it looks like the free faller is accelerating below the planet in place of aiming for the center. It's not helpful the way gravity is typically shown with a bending sheet. This is always the result of 2 combined interactions. Transposed on the free faller, this is the interaction we are observing and using to explain gravity. The system wants to go down, but some continuous force is preventing so. Even more, the approach is caused by the force, not by the interaction with gravity. And when we compare 3 and 4 dimensions, we see how different are the vectors. Because gravity is one force-free interaction. There are more elaborate approaches, such as this hyperbolic geometry, but it's just shifting the problem. For the sake of explanation, we will stick to this kind of representation. We have to keep in mind that some paths will be drawn curving even when they should appear straight. The geodesics is the path followed by all inertial systems conserving momentum. This example is not, strictly speaking, a geodesics, because there are no gravitational interactions or time variations. Yet this is the path the system is tracing without forces in action. With GR, the shape of the spacetime is causing curved trajectories, but geodesics doesn't imply a visible curved path. Curvature is referred to spacetime, and the geodesics is a path on one surface of this geometry. Newton said that every object moves in a straight line at constant speed as part of his first law. This contradicts what we observe with gravity, and if you are looking for a loophole, the error lies in the statement. Conservation of momentum is an intrinsic behavior of each system, while straight line is an abstract concept involving relativities and observations. In an empty universe, I can define my path, and it doesn't matter, since to physics we are conserving momentum when there are no locally measurable accelerations. With some faraway bodies, I can start having an idea for the meaning of trajectory, but my momentum is not conserved with respect to those systems. And so it is of little value also the path I plot using those same systems. Conservation of momentum should not be linked to relativities and limited to what we can define locally. With gravitational interactions, we have curved path and tree acceleration, while we keep conserving momentum. And since we can't locally determine the influence of a gravitational field, we find ourselves at the same time with two contradicting yet indistinguishable situations. So uniform velocity and straight paths shouldn't be part of the first law, since they exist only for us who can observe, remember the past, and anticipate the future. To conservation of momentum, these two paths are equal. Because of the gravitational interaction, the two systems will approach at ever-increasing speed. These geodesics are showing tree acceleration and are still conserving momentum. However, there is also 4 acceleration. This is a true acceleration. It's locally measurable and it causes apparent curved trajectories. Non-inertial frames combines the distortions of 2 accelerations, and one of these is local to the observer. These paths are still geodesics, but they exist only for this specific observer. With GR we are looking for a single framework to handle all types of frames, but to do that it was necessary to discard the absolute nature of measurable acceleration. Within General Relativity, gravity has no force, cause nothing has force. Everything is space-time curvature. These paths don't exist locally, they are apparent because of the acceleration of the observer. Yet, together with the gravitational interaction, they are part of one single space-time curvature. We still retain agreement from any reference frame, but we are removing a piece of cause-effect relations and making the framework underdefined. It doesn't change if it is the rocket to accelerate or the other two. We can infer the difference, but the model doesn't. There is just some amount of curvature between observer and observed systems, regardless of the causes. We don't tell anymore where the curvature is due to a force or if there is a force at all. We can assume if the curvature is due to 3 or 4 acceleration or a mix of the two, but the framework doesn't help you define it, even though it's quite a thing from a physical perspective. Without absolute motion, GR discards all forces. giving up the difference between gravitational interaction and Newtonian dynamics. The model takes all form of energy from any relativity to define the space-time geometry. This flow inevitably affects the equivalence principle. The equivalence principle states that for any small region of space, the effects of gravitation are the same as those from acceleration. Examples like these are typical. A falling object behaves exactly the same on a planet or in an equivalent accelerating frame of reference. If we consider the equivalence from the point of view of a mass, the inertia shown against an accelerating force is the same of the gravitational interaction. The resistance to the force is equivalent to the one in interaction between masses. Thus, inertial and gravitational mass are the same. But gravitational acceleration is not comparable to Newtonian accelerations, since the two interactions don't share the same mechanics and gives different observations and experimental results. This example can be misleading, since both cases the non-inertial frame is not because of gravity, but because of a Newtonian force. If I take two different types of propulsion, both generating 1g of measurable acceleration, we can state these two frames are equivalent, but to formalize it, I would have to list all types of interaction that could generate this frame. The list is virtually infinite, but it definitely includes the observer on Earth. This frame is non-inertial just as many other. You might be tricked by the negative acceleration, but they are all caused by Newtonian interactions against conservation of momentum. Which momentum we are conserving is irrelevant, and this includes motion because of gravity. Indeed, we must remember that force is not action of motion, but action against momentum conservation. To summarize, the equivalence is about the inertial mass, while the observer on Earth is just another non-inertial frame, so that the two looks the same because they are both under the same magnitude of force, regardless of gravity. Newtonian and gravitational interactions are not interchangeable since they cause two different types of acceleration with two different kinds of reference frame. Rotations with centrifugal and centripetal forces are more tricky, and these non-inertial frames differ even from linear accelerations, so that they are not equivalent. Newton bucket is also mentioned without going further because rotation would be too long. Besides giving up the origins for the motion of a system, the right term of Einstein's equation encompasses almost all forms of energy, motion included. Based on the well-known mass-energy equivalence, within GR all forms of energy contribute to the space-time curvature, and implies, for example, that light waves can interact. With no need for matter, they can deflect each other's path. The equation should also mean that a red hot object weighs more of the same colder one. They are two different effects, both really hard to test because gravity is very weak, but what we think happens with each case reflects what we think is the cause for gravity. Einstein's equation is an excellent tool for comparing different forms of energy, so I can say that this hydrogen atom is equivalent to some amount of light waves, but this is a quantitative evaluation. It doesn't make the systems interchangeable. So even if we say these three systems are carrying the same amount of energy, it doesn't mean they are all capable of emitting the electric field of these electrons. Thus, they are not qualitative equivalent. By the same token, there is no implicit reason for every form of energy to be responsible for gravity just because masses do it. Anyway, matter plays such a dominant role in determining gravity that in practice we add values to the invariant mass to get the overall curvature. One of these values is velocity. The change in energy from speed is defined by the gamma factor and Lorentz transformations, and as a consequence within GR, both energy and curvature increase. The greater the relative velocity, the heavier is the system, and the stronger is the gravitational interaction. A faster system will show more relative inertia in interaction with external forces, as well as more energy in a collision. But here is more subtle. Because of the covariance and the arbitrarity of frame, with GR any observer can assume itself stationary, since the overall curvature remains the same, but the gravitational interaction is always symmetric, while the curvature is not. The independence of frame let the observer define the velocity of another system. This is not just increasing the strength of the interaction, it's also increasing the intrinsic inertia of such system. From Earth, the rocket is moving and so increasing both gravitational interaction and its inertia. And the opposite is also true, neglecting that the same velocity over different masses gives two very different increases of energy. It follows that if I have a rocket expressing constant thrust, when I look from the point of view of Earth, the rocket has more inertia, and so it should locally measure a lower acceleration with respect to when I use the rocket as reference. According to the relative velocity between the two systems, the faster the rocket goes relative to Earth, the less its constant thrust should be effective in accelerating the system. But from the point of view of the rocket, this makes no sense, because it is the Earth that is moving, therefore it's the planet that should have more inertia. So, according to the frame we choose, the rocket measured two different values for its local acceleration. We can see this in another way. Starting from far away with the same uniform acceleration, when I pass by the planet, should I measure a decrease of the local acceleration because more inertia makes the thrust less effective? If the gravity of the planet can actually affect my inertia, it means that from just this effect, with no external references, I can tell the presence of gravity and quantify my relative velocity. We can allegedly measure the effect of velocity on the interaction, despite it should be on the planet. However, this is possible only with non-inertial frames, thus Newtonian and gravitational interactions are not equivalent. It also means that velocity is not entirely relative, because even when I am the reference, some speed cannot be assigned to other frames. So we break GR with absolute motion. No means that the measured acceleration remains constant, so speed of light is not what we think, and no relative velocity can affect my inertia. And we break GR. C is never locally approachable, so it can never be a limit. One might question about the speed. Maybe it should be accounted from the beginning. But that would mean my inertia is affected by the planet even when I'm out of its gravitational range. And we become Machian. So this is some of the slippery with GR having energy and inertia from velocity together with the arbitrary frame. Beside this kind of interactions, Einstein equation is broadly explained with energy tells space how to curve and space tells masses how to move. The curvature of each mass won't participate to its own movement. Each system is contributing to the overall space-time curvature and affects how the other moves. The effect must be combined with the velocity of each system. This velocity is additional to the movement from curvature, but it affects the shape of that same geometry. So, as example, the curvature of C, defining how other systems are moved, also depends on its velocity. Meanwhile, its trajectory combines its own velocity and the interactions with A and B. The movement of each system depends on the others, but the movement of the others is affected by our movement. The situation escalates quickly because these effects are reciprocal for all of the three. Each system is at the same time depending on and defining the movement of the others, with 4 dimensions. While there are specific cases in which Einstein field equation is completely solved, more broadly, two bodies interacting is already a problem, and we need to make approximations. By introducing a third one, we can't properly handle the model, and we are stuck. The last term of the equation we left out until now is lambda. This part is the metric tensor for the spacetime geometry, and lambda is the cosmological constant. It was initially used to balance the effects of gravity and was later abandoned also by Einstein. It has been reintroduced since we currently speak of accelerating expansion for the universe, and we don't consider gravity capable of what we observe. Thus, we introduce dark matter from galactical scale and dark energy on universal scale. We can measure gravity, give it a cause, and see it conserves momentum, while everything else is deduced from observations. We add some extras here and there until the pulling effects of gravity and dark matter are counteracted by dark energy, represented with the cosmological constant. The acceleration is still under debate, and no cause is found for these dark components. But we are deducing by our understanding of gravity. If we don't understand gravity, our models are wrong and gives us artifacts. The question can also be faced this way, but there are hints about a problem with our understanding. GR is not affixed to Newtonian gravitation, but a different approach. It handles relativistic effects, removes the action at distance, and correctly predicts lensing. Yet for as much agreements, the model already struggles with two-planet orbits, and the increasing complexity with topology in place of the symmetry with inverse square law in many cases is not repaid by the increase of accuracy. Also because it's dropping absolute motion. Any case beyond the size of a solar system, none of our model can deal with reality. Trying to derive a single framework for every motion are emerging problems with the equivalence. Non-inertial frames are measuring acceleration being under some Newtonian interaction. Gravity is a field interaction that remains within inertial frames and has different dynamics. Not every acceleration is the same, but they are treated equally, both converging into spacetime curvature. Conservation of momentum of the first law is comparable to flat spacetime, and both inertial conditions refer to force-free systems following the path of least action. Macroscopic motion in our universe is at least the combination of two types of frames with two kinds of interaction. Gravitational and Newtonian coexist and concur to what we observe, but they have different features, and the accelerations of the Newtonian interactions lead to non-inertial frames with different observation and experimental results. So curvatures resulting from accelerations are not all the same, and some velocity are less relative than others. Issues with representation are just one side of a much bigger question about our modeling and understanding of gravity. If at this point things still don't work out, it's because there is a lot to unfold yet, and one problem is with the speed of light.